Hello, thank you very much for the introduction there, Alina, and thank you everyone for joining us this afternoon. My talk is about human thermoregulation and specifically to do with the current climate that we're in at the moment in our changing world. So I'll start a little bit about my own pathway to academia. I started my degree in sport and exercise science at the University of Brighton, and I studied there, graduating in 2014. I went on to study my PhD in environmental physiology and specifically investigating the physiological and inflammatory consequences of fire exposures and working practices of fire and rescue service personnel. I was a self-funded PhD student and part-time, so I worked alongside this as a laboratory instructor and doing some visiting lecturing hours. And I got involved in projects alongside my PhD as well, and I was doing some lab work in terms of heat chamber work in the university, and also lots of field work going out to fire training centres too. During my PhD, I tried to network as much as possible, and thanks to the PhysSoc travel grants, I was able to go to a few different conferences and really get to meet other people, which was great. I stayed on at the University of Brighton after I graduated at the end of 2018, and I did an extended bit of project work based on the work around my PhD while I was looking for a permanent position. I then moved on and joined the University of Roehampton in September 2019, which has been an interesting start to academic life with the change to teaching online and COVID lockdown, but it's been really good so far. Someone who has kind of recently been through the PhD process and now as an early career researcher, my key recommendations for those that would perhaps like to follow a career in academia would be to, as standard is advice, publish as you go and to kind of get as much teaching experience as you can if that's something you're interested in. But I would also recommend talking to people and trying to find somewhere that is a good fit for you as well. I'm more than happy to talk more about these kind of areas or to kind of answer questions on that at the end if it's helpful to anyone. So on to what I'm actually talking about today. We'll start off with a little bit of a background information into thermoregulation for those of you that aren't environmental physiologists. Then a little bit of information about why it's relevant to the world as we know it at the moment. And finally discussing how this might impact some special populations and what interventions there are that we can actually do about these things and help these populations out. So that's kind of an overview of the talk today. So if we start off at the beginning in terms of thermoregulation, our body gains and loses heat through numerous different key mechanisms. And on this figure here, they're demonstrated in the arrows that you can see. So we can lose or gain heat through things such as convection, conduction, radiation, and evaporation. And our body is able to produce heat itself. So this is our metabolic heat production that we produce on our own. And these things all come together to form the heat balance equation, whereby our body ends up storing or losing heat as a consequence of its gain of heat through radiation, conduction, convection, and also through the loss of heat with evaporation, so the E on the end there. Our body typically maintains a core temperature of around 37 degrees Celsius, and this varies throughout the day by about 0.5 degrees as well. In circumstances of heat or cold exposure, we're actually really good and capable of thermoregulating to defend that core temperature. We can detect changes in temperature via thermal receptors in our skin and our central nervous system, for example, and this information is relayed to our hypothalamus and cerebral cortex in the brain. Our hypothalamus contains what we might call the thermoregulatory center. And this center enables us to send messages via the sympathetic nervous system to effector organs to bring about responses to this change in temperature that we're detecting. Now, these effector organs can be things such as our skin arterioles. So we can dilate our blood vessels around our skin. So if we get a hot stimulus, we can vasodilate, cause blood flow to increase to our periphery. Vice versa, if we're cooler, we can vasoconstrict. We can also stimulate skeletal muscle and cause that to start contracting and causing shivering if we're cold. We have sweat glands too that we can stimulate a sweat response. And so that means that we can evaporate that sweat off the skin. And this is our key mechanism for heat loss and is particularly important when we're doing things such as exercise. We also have behavioral thermoregulation, which isn't on my figure. And this is where we choose consciously to add or remove layers of clothing or to remove ourselves from a heat source. And the combination of these effector organs all result in changing or preventing change to our core body temperature. So if we take a situation of thermal heat stress, so it's getting hot, we end up with an increase in sweat rate. We also get an increase in skin blood flow towards our peripheries. This causes us to have a reduction in our stroke volume, and so an increase in our heart rate to try and combat this. So we've now got some cardiovascular strain going on as well. We get a reduction in our thermal comfort. If you think back to if you're in a really hot situation, you don't feel very comfortable, you're not very happy in it perhaps. And this might lead to a reduction in drive to actually want to do any kind of activity and exercise as well. We have kind of a few different theories around what happens as a consequence to this and how this is all controlled. The central theory to do with thermoregulation suggests that the hypothalamus activates these heat loss mechanisms. We kind of activate to try and lose heat, and we do all of these things to try and protect our body. And essentially, we purposely reduce our workload to prevent our body from getting too hot. So we get a massive reduction, perhaps, in work performance. So reducing our workload to prevent getting too hot. If, however, we're in a scenario where we can't reduce our workload, we might end up in the realms of the critical core temperature theory. And this is where we have 41, 42 degrees Celsius in our body, and we're just unable to continue functioning at this point. In either scenario, we end up with a reduction in our work performance and our capability to be physically active in heat. But it's not all just about work performance, it's also about ill health as well. So in heat stress scenarios, we can experience heat illnesses, and they can range on a continuum of severity. So if we start at the beginning, we might have things such as heat cramps, heat exhaustion, we might feel quite fatigued perhaps, but this can progress on in severity. And if we get to the far end where we're in our heat stroke, this can potentially be much more severe and even fatal. So heat stroke typically occurs when our core temperature exceeds around 40.5 or 41 degrees Celsius, and it's combined with some form of cognitive dysfunction. So this is where you might have confusion, loss of consciousness as well. And without rapid removal from the heat source and rapid cooling, heat stroke in this scenario can actually be fatal. Now, if we think about the world around us at the moment, global warming has resulted in an overall increase of about 0.8 degrees Celsius during the last century. And this nice little video that you should be seeing on your screens now shows the changes in temperature with a colour across those years. And this increase in temperature has actually led to an increase in the number and intensity of heat waves. Now, heat waves typically refer to temperature increases around 5 to 6 degrees Celsius above the normal temperature range for a region, and are typically counted when they occur for 3 or more consecutive days. Now, between 2000 and 2016, the number of people exposed to heat waves increased by around 125 million individuals. A prediction of a 1.5 degrees Celsius increase in world temperature would mean that around 14% of the world population would be exposed to severe heat waves at least once every 5 years. If we increase this projection rather than 1.5% increase in temp to 2 degree increase in temp, we actually get almost a 37% number of the population. So this is a difference around 1.7 billion people. Current emissions threaten that actually we're possibly going to be above the 2 degree increase in temperature. So that's an awful lot more in terms of the number of people and that are going to be exposed to these severe heat waves. And we might be able to see this in what's going on at the moment. So recent news reports, we've got things such as the Arctic burning and wildfires up in the Arctic Circle in Greenland, new records of temperatures noticed in the Arctic. And also in countries such as India, a recent report came out there of around a 3 to 4 times higher frequency of heat waves predicted in the future. Now, the reason this is important is because heat waves have been linked to cause an increase in heat-related mortality. If we take the 2003 heat wave in France specifically, temperature exceeded its norm by 11 to 12 degrees Celsius for 9 consecutive days. And over the period of August, nearly 15,000 deaths occurred in excess of the norm, and this was a 55% increase. These deaths represented a 20-fold increase in deaths directly related to heat stroke and dehydration, but also an increase in deaths associated with circulatory and respiratory diseases too. If we look broader than just France, we see between 2003 and 2019 in the UK, there averaged around 800 to just over 2,000 deaths excess a year because of heat waves. We also see across European countries that 28,000 people die every year due to heat waves. And if we also look aside from just Europe, if we take India, for instance, in 2010, there was a 41% increased mortality rate due to heat waves. And on average each year, if you take non-heat wave and heat wave days, 18% increase in mortality occurs in heat wave days. Now, if heat wave predictions continue as suggested, it's likely that heat wave related excess mortality is expected to increase the most in tropical and subtropical countries. So not just a European issue, a worldwide global problem. But there are some individuals that might be particularly at risk compared to others. So if you take the elderly, for instance, in 2003 heat wave that we just spoke about in France, if we look at Paris, the recorded 2,814 deaths that occurred. Of these, 81% were from elderly individuals. So, sorry. So if we take recorded 2,800 deaths, and of those 81% were from the age 75 and over. The number of people worldwide aged 65 and above is predicted to rise from 700 million at the moment to around 1.5 billion in 2050. So that's 16% of the world's population. So not only are we at the most at risk population, but the elderly are also likely to increase in the amount of size they are in the population too. Now, elderly individuals store more body heat than the young do, and they are more likely to be at risk. Milliard et al. Recently produced a really nice review paper that looks at the associated issues to why elderly might be more at risk to heat exposure. And this figure goes through a really good summary of that. So if we start off, we have attenuation in our sweat response, so our pseudomotor function is reduced. We are less able to produce as much sweat at each gland, and our elderly also have a delayed onset of sweating threshold. So this means that it takes a higher core body temperature for them to actually start sweating. The elderly also have a reduction in their cardiovascular function, so their total body volume their total blood volume decreases. They have a reduced blood flow and a decreased ability to vasodilate. And this means that their ability to actually cause that loss of heat through that skin blood flow redistribution is reduced too. So we've got reduced heat dissipation. We also have some other issues with the elderly that also might come into play. So the elderly are more likely to have a reduced immune function, and they've been reported to have greater gut permeability and cytokine expression, which means they might have a state of inflammation. Now, things such as gut permeability have been increased or noted to be increased by heat stress situations. So endotoxins are released from the gut and go into circulation, and this can cause an inflammatory state and has been linked to occurring when heat stroke occurs too. Now, if our elderly individuals have already got an inflammatory status or reduced immune function, it might mean they have a reduced ability to actually cope in these scenarios. And the other important aspect to consider with elderly individuals is that they have a reduction in their behavioral thermoregulation. They have a diminished perception of discomfort in the heat, and they also have a reduced thirst stimulus too. So they're less likely to actually initiate those behavioral thermoregulations kind of activities that we were talking about. So if you add all of this together, you end up with an increased risk of a heat illness and potentially an increased mortality rate during these heat wave scenarios. Another population that might be important to consider is those that occupations that actively work in hot environments, but also those that wear personal protective equipment, so PPE. Now, these might be firefighters, for instance. You're getting a hot stimulus from the environment and you've got PPE. It might be individuals working in body armor, or if we take recent situations, those that are working to protect individuals from and working in infectious diseases as well. Now, the issue with PPE is that actually you're stopping the main form of heat loss being evaporation. If you've got this protective layer over the top, your ability to evaporate sweat is greatly diminished, and therefore we end up in what typically is called an uncompensable heat stress environment. So our body temperature just keeps on increasing. And if we think about these occupations, in many scenarios, they can't actually behaviorally thermoregulate. They can't remove their PPE and they can't reduce their physical work because of the situations that they're in for their jobs. If we take an example from firefighters specifically, we can see here this is a trace of core temperature and heart rate across a day of training of live fires. The dotted box zone here that you can see represents a live fire that we know about, and the red line that you can see is our increase in our core temperature. So we see a peak in that around 38.4 degrees Celsius with this fire exposure. You also then have an orange jagged line on your screen, and that represents our changes in heart rate, and that gets up to 182 beats per minute. So we're getting some kind of physiological strain, cardiovascular strain, and our individuals are getting hot, but not really to an at-risk heat stroke level from this exposure. And what's really actually interesting is that this individual didn't just do one exposure this day, they did a second. And if you look at this bottom section here, they've had almost an hour and a half of resting period in between these two exposures, and yet core temperature still hasn't reduced down to its resting level at the end of it. When you look at the next exposure, so we look up to that next peak, our increase in core temperature has gone up slightly higher this time to 38.54 degrees Celsius. So they're getting hotter the second time they're doing work because they haven't managed to get back down to resting. Now this occurred when the individual was allowed to rest for quite a long time between. They could remove their kit, they could rest in a cool area, and they could appropriately rehydrate. If we were to increase the ambient temperature, so no more cool resting, if we were to do that, we might end up seeing the core temperature increase even further on this second exposure, or it might mean that if we can't have a shorter entry time, they're more at risk of high risk of heat illness, or actually if we do have a longer entry time, you might need more staff to be able to facilitate the activity that's occurring. So what can we actually do about all of this? Well, there's a few different options. Heat acclimation is one of those possible options. The human body is capable of adapting to heat, and heat acclimation is the process of experiencing repeated heat exposures over numerous days. And this can result in improvements in performance in the heat. It can reduce core temperature, reduce heart rate, and increase sweat rate. Heat acclimation typically results in adaptations after 4 or 5 days, but as you can see from the figure on your screen, it typically takes around 10 to 14 days to really maximize those adaptations. Once you stop those heat exposures, those responses and adaptations slowly reduce back down to normal. So it's not something you can continually maintain if you stop your exposures, but it is suggested that if you have a period of acclimation, say 10 to 14 days, you stop exposures and then do another period of acclimation for say 4 days, that second amount is sufficient to increase your adaptation levels to what your previous version was. So it's much shorter the second time around to re-acclimate, so it's called. If we take an occupational perspective on this, we know that instructors experience high exposure levels of around 10 to 40 times a month, and we know that they can develop an acclimated state. This figure here shows you a core temperature continuum, and this is what their core temperature response is at the end of a heat tolerance test in our lab. And our triangles on here are our instructors compared to our control group, which is our circles. Now our instructors tend to be at the cooler ends, this is their end core temperature, down at around the 37s compared to our control group who sit further up on that continuum. So our instructors actually had on average a 0.2 degree lower core temperature in response and also an increase in sweat rate. However, experiencing such high temperatures on such high frequency, we think might actually be leading to a maladaptation in our instructors, whereby they're exhibiting almost a chronic systemic state of inflammation, and this may actually be linked to some symptoms of ill health that they might be experiencing. So keeping workers in a constant state of acclimation really likely isn't possible and could actually lead to other consequences too. So if we then look at the elderly individuals that we're talking about, short-term heat acclimation has been found to not elicit adaptations. A nice study by Danon and co showed that similar core temperature responses occurred between control groups and with an acclimation process. This might possibly because the elderly individuals weren't able to sustain such a high exercise workload needed as a stimulus. Also possibly the duration of the acclimation wasn't sufficient enough to see those adaptations. Theoretically, longer periods of acclimation could possibly overcome this, And passive heat exposure via a bath has also been suggested as one of those mechanisms, kind of interventions that may help if you can't get elderly individuals to exercise at quite a high work rate. Hot water immersion has been suggested as helpful for an exercise process, so 30 minutes of exercise and then hot water immersion afterwards. But it's not really clear how well this would work just passively without the exercise first and with an elderly population. Theoretically, it's something that could be helpful and practically something that the elderly could do. We just don't know yet how beneficial it might be. And there's also obviously safety considerations to think about as well, in terms of things such as the risk of occurring a heat illness themselves, and also if elderly individuals are doing this on their own, is it a safe thing to occur? And how would you monitor and help these individuals? So that's the kind of more long-term aspect, I suppose, in terms of heat acclimation. But there are some more acute heat alleviating interventions that we could use. So the majority of deaths associated with heat illness can actually be prevented. Behavioural thermoregulation is likely the key aspect to this, specifically in ensuring that individuals have a cool place to live and reside, especially during heat waves. This might seem like a really simple thing, and aircon systems is quite common in hotter countries, but it's quite unusual to have air conditioning in a lot of homes in a lot of other countries. And if we think specifically about the pandemic scenario that we're experiencing at the moment, this could also exacerbate issues like this. So if you can imagine you've got a heat wave in your country, like many individuals have done recently, they're then living at home in a house with limited ventilation, no air conditioning, and they're unable to leave. So something as simple as air conditioning or appropriate cooling options could be really beneficial. We also have things such as simply being hydrated. We know that dehydration increases heart rate and increases core temperature, and this is particularly important during exercise as well. For the elderly, we've spoken already that they have a reduction in thirst sensations, and so they're likely not to be having an adequate fluid intake. So making sure that hydration is kept up is a really simple tool. We also then have acute cooling methods. There's an absolute abundance of research into the benefit of different types of cooling methods out there, from cooling vests, phase change materials, ice slurries, that all suggest these things could be beneficial at keeping individuals cool. We looked specifically at the use of ice slurries as a pre-cooling method for firefighters, and we identified that it was the most effective cooling method for reducing core temperature before an exposure, with it reducing by about 0.4 degrees Celsius. There's also been quite a nice study that came out recently by Mali et al. And they looked at different tolerance times whilst wearing personal protective equipment with different cooling methods. And they found that ice vests, slurries, combination cooling, water perfused suits, they all reduced the cardiovascular strain that was being experienced. But actually the combination cooling, so using ice slurries and an ice vest, increased tolerance time, and so did water perfused suits. And this tolerance time increased from around 17 to 23 minutes. So actually improving the work capacity of your employees by using some of these mechanisms, which could be really helpful. Another aspect that I think is really key in this area is actually education. As behavioural thermoregulation is kind of the main thing we can do to prevent mortality, it's actually really important that we share this information and help those that it is really necessary and kind of the individuals that really need this. And this may be as simple as making sure that individuals understand the heat warning systems in their country, they're aware of the help that is available for them, and they know what to do if they actually have a heat illness, ideally before it escalates into a heat stroke scenario. I quite like this that I came across recently, that the City of Toronto has announced they have cooling centres in place. So areas that are welcome to everybody, they are air conditioned, so individuals can seek that shade and that cool area. Water is available to them and they can get first aid if needed. And I think that's a really good idea to be able to support those who perhaps need this assistance but don't have it as access at home. I think other key points to consider are also education to do with the importance of physical activity and having a healthy body fat percentage to reduce heat illnesses. And also things such as ensuring those populations know how to check their hydration levels. So quite simple interventions that could be helpful. Recently, we've been working with the Fire Brigades Union here in the UK to create an educational course that's now available to firefighters, and it teaches them and gives them knowledge about heat illnesses, and also gives research-informed advice about how to prevent and how to actually treat these illnesses. So user-friendly dissemination of this information to help educate those that might be most at risk. And so to kind of summarize this presentation, the key points really to think about and take away are that humans are highly capable of defending their core body temperature, and they're capable of adapting to environments given time. But with climate change, there is an increase in the severity and frequency of heat waves, which is something that is difficult for individuals to perhaps prepare for. And these increase in heat waves comes with an increase in mortality rates. Those specifically affected might be the elderly in terms of risk of mortality, and also those who work in hot environments and wear PPE for their occupations. And finally, I think education is one of those most important aspects that might actually help those populations, and making sure we're really sharing the information of the research that we're all out there collecting. I'd like to just end on this image, which is by Professor Ed Hawkins. The coloured stripes represent the changes in temperature that have occurred in the world since 1850 until 2019. I think it's a rather beautiful and pretty scary dissemination of some important information. I'd like to thank PhysSoc and also to the organisers for this great virtual conference and for inviting me, and also to thank the University of Roehampton and the University of Brighton, who have supported me through my academic journey, and those who have collaborated on research with me so far. I'm more than happy to take any questions.
Thank you. Thank you, Emily, for a really interesting talk. We have time for a few questions now, but I want to remind you that the mental health workshop is starting in 2 minutes. So you're free to just switch over there when you want, or you can stay here and hear the questions. We have
Sorry about my phone ringing partway through.
It's okay. We have a number of questions, so we'll just get started. We have one from Moritz Egelbusch at the, I probably can't say it, but the Vrije University in Amsterdam. What are your thoughts on voluntary heat exposure, such as sauna use for health and longevity?
Yep, I think we're talking, it comes into two very slightly different things. I think there is some research out there that suggests that sauna use and heat from a health perspective is useful and helpful. I'm not sure if Hannah Palabinsky is going to cover a little bit of that perhaps in her talk, but the benefits for it in terms of cardiac disease risk as well. But I suppose we're talking here short-term exposure of not too high a temperature and no exercise at the same time. And that's something that's quite different from high physiological strain that you're undergoing in kind of perhaps those that are more high at risk in terms of the elderly or those in occupational settings. So I think if it's more about the way that heat is being applied and kind of the type of exposure that individuals are getting.
Thank you. Now we have one from Iola Offusat. Sorry for the pronunciation. Thank you for the excellent presentation. When a heat acclimatized individual moves to a cool environment, can it be dangerous to his or her health?
If they move to normal temperature environments, then no. There's evidence that suggests that actually heat acclimation doesn't do any damage to performance in normal temperatures and actually could be beneficial. Extreme changes in temperature from heat to cold, that's obviously something slightly different, but in most cases the body reacts as fine. It just might lead to slightly more cardiovascular strain in the initial kind of change.
Now we have one from Abdul Ansari, and I think he's from Taxila American University in Guyana. Very nice presentation and more relevant to day-to-day life. What is the threshold temperature at which the human body starts responding to increased temperature?
Yep. So we typically have a thermoneutral zone, which I didn't cover because Dr. Palabinsky will be covering in her presentation. So our thermoneutral zone is adaptable and can change with kind of gradual increase in changes in temperature. It will depend very slightly on the different individual themselves, but we might see a sweat response occurring at, say, the 37.5, so 37.8. So it doesn't take a great deal percentage kind of degree increase in temperature to start seeing that stimulus, but it more depends on the change from where you are at rest to that increase in temperature to get that stimulus to occur. Because as I said, your body temperature fluctuates throughout the day normally. So it's that extra stimulus that's causing that change.
Thank you. We have one from an anonymous attendee at the University of Bath. Are you aware of why the elderly exhibit a lower thirst response? Is there a safe way to increase thirst in the elderly to encourage them to drink more without actually dehydrating them further in the first place? I assume that the current recommendations would be to make elderly aware of their reduced thirst so that they could set themselves reminders to drink regularly, particularly during times of excessively high temperatures.
Yeah, I think that's an absolutely great point. I think targeting the elderly in terms of setting them specific things that they can actively go and do to encourage them to drink is definitely important. And I think that's a great suggestion to enable them to actually be able to kind of not overcome that decrease in thirst stimulus, but actually they're consciously aware of it. And I think that's where the education part comes in there.
Now we have one from, no, we answered that. We have one from Megendra Ameta. Sorry for that again. Does regular heat exposure increase heat tolerance, and to what extent?
Yeah, so that's essentially the point of our heat acclimation. So regular heat exposure will increase your ability to actually be able to cope in the heat. And it does that through the numerous different mechanisms of increasing plasma volume, increasing your ability to sweat, and so reducing your heart rate and core temperature response.
Now we have one from Manisha Mavi. Very nice presentation. How can we manage this? Here in India this year we had a very unusual weather in summers. In day-to-day life, how can we acclimatize to such adverse conditions? Yeah,
so in day-to-day life, I would suggest there's a lot of those acute interventions that can kind of help out. So ensuring you have those cooler aspects or cooler areas that you know you can use. Using things like being hydrated. You can ensure, you might not have access to an ice slurry machine, but you might have ice lollies or cold water that you can take in rather than just normal temperature. So those small things that you can do to help you feel better and to kind of cool you down as well. Over time, we can adapt to these changes in temperature, but having a sudden increase, which is what we're talking about with these heat waves here, isn't something that we can just magically adapt our body to straight away.
Thanks. We have time for one more question. So we'll take this one from Emma Clare from the Manchester Met University. What are your thoughts on time of day exercise, physical activity in relation to heat gain, heat loss mode of the body? And is this more or less relevant in hot climates?
I think you do see with the change in temperature across the day, so your normal circadian rhythm, that in some cases, we particularly see this in some of our firefighters, that if they're doing an exercise in the afternoon, their core temperature response is higher because they're starting off higher. So this does seem to migrate to the other parts of the day. And it might mean that some individuals, I suppose, in a heat stress kind of heat wave scenario might be slightly more at risk in those kind of higher parts of the hotter parts of the day in terms of their core temperature normal rhythm. I hope that answers the question.